Hello students, this is Dr. Anita Raj welcoming you for an important session in solid state. Today we shall see what are Schottky and Frenkel defects in crystalline solids. So before starting to learn, you should know what is a stoichiometric crystal first, right? So what are stoichiometric crystals? See, the crystal in which cations and anions are exactly in the same ratio as indicated by their molecular formula termed as stoichiometric crystal. See, in a crystal, so always in a crystal there will be cations and anions. But in a stoichiometric crystal, both these cations and anions will be of same number. Okay, it will be in same ratio. So when if that is the case, we call that crystal as a stoichiometric crystal. Okay. Then what do you mean by a stoichiometric defect? So the defect which do not affect the stoichiometric composition of a crystal are called as stoichiometric defects. So whenever there is a defect in a stoichiometric crystal, obviously there won't be any change in the number of cations or anions in the crystal, right? So if that is the case, then that defect is called as the stoichiometric defect. Okay. See, let us see the different types of stoichiometric defects now. The first one is a Schottky defect and the second one is a Frenkel defect. See, actually these two, Schottky as well as this Frenkel defects, are seen in ionic compounds. Okay, we can see this type of defects in ionic solids, right? See, actually two more types are also there. They are the vacancy defect and the interstitial defects, and they are seen in non-ionic compounds, and we can see those type in my later classes. By the by, what is Schottky defect? Actually, this defect was first discovered by the scientist. He's a German scientist, and his name is Schottky in 1930. Okay. Actually, this Schottky defect arises when equal number of cations and anions are missing from their lattice sites, leaving behind a hole or a vacancy. See, actually this is a stoichiometric crystal. See here, equal number, see this small one is the cation and the large one is the anion. See, when equal number of cations and anions are missing from their lattice sites, and since they are missing, we can see a hole or a vacancy in that particular place. If that happens, then we call that type of defect as a Schottky defect. Okay, when equal number of cation and anions are missing from the lattice sites, and obviously when they are missing, a hole or a vacancy will be created. Okay, so that type of defect is called as Schottky defect, right? See, in which places we can observe this Schottky defect. Schottky defect is observed in strongly ionic compounds. Okay, they are observed in strongly ionic compounds with high coordination number. What do you mean by coordination number? Actually, it is the number of atoms nearest to a atom in the crystal. Okay, number of atoms nearest to an atom in the crystal. For example, if this is the cation, see here how many atoms are in contact with this? 1, 2, 3, 4. Okay, so likewise, so if we are taking this one, you see here when we are taking this one, this is in contact with 1, 2, 3, 4. Okay, so 4, the coordination number of this particular stoichiometric crystal is 4. Okay, see, if the coordination number of this ionic compound is very high, then we can expect this Schottky defect. Okay, and the next criteria is which has cations and anions with almost same size. See, if a stoichiometric crystal is having cations and anions of almost same size, not the same size, but almost, okay, with a meager difference, then we can expect Schottky defect there. Okay, and see here some examples are there. Examples for this type of crystals are NaCl. Okay, we can expect Schottky defect in sodium chloride. We can expect in potassium chloride, then potassium bromide. Okay, and then cesium chloride. Okay, cesium chloride, then silver bromide, right? So these are the different types of crystals in which we can observe this Schottky defect. Actually, 1 centimeter cube of NaCl, 1 centimeter cube of NaCl, right, will be having 10 to the power 22 ions. Okay, it will be having 10 to the power 22 ions, in which 10 power 6 Schottky pairs are there. Okay, we can see 10 to the power 6 Schottky pairs. Okay, Schottky Schottky, right? Schottky pairs can be observed, right? Schottky pairs can be observed in 1 centimeter cube of NaCl, okay? Thus, there is one Schottky defect per 10 power 16 ions, understood? So, one Schottky defect can be seen in 10 to the power 16 ions, understood, students? So, the next important thing is consequences of the Schottky defects. So, what are the significances? What are the things happen when Schottky defect is observed in a crystalline solid, okay? The first one is density of the crystal decreases, okay? Well, how come the density decreases? What do you mean by density? How to calculate density? See, density is represented by the term rho. Density means mass by volume, am I right? Mass by volume. This is the general formula, right? Mass by volume. See here, in this crystal the volume remains the same, but the mass will be getting reduced because one cation and one anion is missing from this place. Since the cation and anions are missing, obviously the mass will be getting decreased. So mass by volume, obviously the density will be decreasing. Understood, students? The reason why density of the crystal is decreasing due to Schottky defect. Okay. Next one is lattice energy decreases, thereby stability of the crystal decreases. Okay, what do you mean by lattice energy? Actually, this lattice energy measures the strength of the ionic bonds in an ionic compound. Okay, it measures the strength of the ionic bond in an ionic compound because it is the amount of energy required to break the ionic bond. So, lattice energy is the energy required to break the ionic bond. Okay, so stability obviously depends upon the magnitude of the lattice energy. If less energy is required, obviously stability also decreases. If lattice energy decreases, stability decreases. Understood? So, next one is entropy. See, due to the missing of ions, the randomness increases. Whenever randomness increases, entropy increases. Okay, so due to the missing of ions, there will be randomness, we can see in the crystal, so automatically entropy increases. Understood, students? So, in this we have seen what is a Schottky defect and how it happens, and where we can expect this Schottky defect. We can expect it in strongly ionic compounds with high coordination number, and also in compounds in which the cations and anions are of almost same size. Okay, and what are the things happening due to Schottky defect? That also we have seen, that is consequences of Schottky defect. Okay, so density decreases, lattice energy decreases, thereby the stability of the crystal decreases, and entropy increases. Understood, students? Next we shall see what is Frenkel defect. Okay, so next one is Frenkel defect. See, this defect was discovered and studied by a Russian scientist named Frenkel in 1926. Okay, so when this Frenkel defect occurs, see, this defect is caused if some of the ions of the lattice occupy the interstitial sites, leaving equal number of lattice vacant sites. Okay, see, when this type of defect occurs when some of the ions of the lattice occupy the interstitial space. Okay, so actually what happens is normally cations will be migrating. Okay, normally cations will be leaving their lattice sites and it will be moving to the interstitial sites. Okay, see here the cation, the small ion, the cation is moving from its lattice site and it is taking an interstitial site. What do you mean interstitial site? The space between the other ions. Okay, so it will be occupying the interstitial sites. Because of this type of movement, the Frenkel defect arises. Okay, since the cation is moving to another place, a vacancy is created here. Okay, so now this type of the Frenkel effect is otherwise called as vacancy defect. It's also having another name, vacancy defect. Okay, vacancy defect. Vacancy defect in its original site. See here, a vacancy is being created in its original site. This is the place where this cation was seated, right? So in its original site, a vacancy is being created. So that's why it's called as vacancy defect. And another name is also there, and its name, and the name is interstitial. Okay, interstitial defect. So interstitial defect is created in a new site. Am I right? See here, this is this cation is occupying an interstitial site. So the name interstitial defect, and obviously it is taking place, it is occupying a new site. That's why this interstitial defect is seen in a new site. Okay, and one more name is also there, that is dislocation defect. Okay, dislocation, right? Dislocation defect. So these are the different names given for this Frenkel defect. Okay. Now we are going to see the conditions for Frenkel defect, or else where we can observe this Frenkel defect. Okay. See, the compounds with low coordination number, will show Frenkel defect. And the next one is the size of the anion should be bigger than the cation. Obviously here the cation size is smaller and the anion size is little larger. Okay. This defect is not found in alkali metal halides. Okay. Why this Frenkel defect is not observed in alkali metal halides? The reason is the cations and anions will be having almost equal size, but Frenkel defect can be observed in compounds in which the size of the anion is a little bigger than the cation, is it not? But in alkali metal halides, both the cations and anions will be having almost equal size. See, if that is the case, then the cations cannot be accommodated in the interstitial sites. Okay, if all the cations and the anions are of same size, if the cation is released from this place and it cannot occupy the interstitial sites if all the ions are of same size. That's why the anion should be little larger than that of the cation, so that this cation can be easily accommodated in the interstitial site. Okay, so let me give some examples in which we can observe this Frenkel defect. See, AgCl, silver chloride, silver bromide, then silver iodide, okay, then zinc sulfide. In all these compounds we can observe the Frenkel defect. See, out of this, the silver bromide is will be showing both Frenkel as well as Schottky defect. Okay, Ag plus ion. Okay, this Ag plus ion is being smaller in size and can be accommodated in all the interstitial sites. That's why these type of compounds are showing the Frenkel defect immediately. Understood, students? Next we are going to see the consequences of this Frenkel defect. The first one is density of the crystal remains the same, whereas in Schottky defect the density of the crystal decreases, is it not? But here the density remains the same. Why so? Because they see here the cation which is missing, which is moving from this lattice, its original site. Obviously it is seen in the interstitial site, that is, it is seen within the crystal, it's not going out. Okay, since the cation is present inside the crystal itself, the mass of the crystal remains the same. The volume also remains the same and the mass also remains the same. So mass by volume remains the same. Understood? Though the Frenkel defect is there, the mass and the volume of the crystal remains the same. If so, the density of the crystal will be remaining the same, because mass by volume is density. Understood, students? The next one is lattice energy decreases, thereby stability of the crystal decreases. This I have explained in Schottky defect, so the same thing happens here. And also entropy increases. Yes, because one of the cation is replaced from its original site, so automatically randomness will be increasing, so entropy increases. Okay, next one is this defect influences the chemical properties of the compound. So obviously that happens because some change, that is cation is moving from its original place, so automatically chemical property of the compound will be changing. Okay, the last one is the electrical conductivity of the crystal increases. Why the electrical conductivity of the crystal increases? Because when a potential difference is applied to this solid, then the ions will be moving from the lattice sites and it will be occupying the holes or the vacancies. Okay, the ions will start to move. Okay, since here there is a vacancy, when you are applying a potential difference, the ions will be starting to move and it will be occupying the vacancies. Such movement is responsible for electrical conductance. Understood, students? Also in Frenkel defect, due to the movement of a cation from its lattice point to its interstitial site, we can observe Frenkel defect. Okay, and Frenkel defect is observed in compounds with low coordination number and in compounds in which the size of the anion is bigger than the cation, and this defect is not seen in alkali metal halides, and I have given the reason also. Okay, and what are the consequences of the Frenkel defect? Density of the crystal remains the same, lattice energy, thereby the stability of the crystal decreases, entropy increases, and this defect influences the chemical property of the compounds, and the electrical conductivity of the crystal also increases. Understood, students? Well, fine, students, you might have understood what is Schottky defect and Frenkel defect from this class. Would meet you with another important topic in a short period. Until then, it's Dr. Anita Raj signing off from you. Thanks for watching.